Welcome to our introduction on demystifying neural networks. Deep learning is a powerful type of artificial intelligence. It allows computers to learn from data in a way that's similar to how humans learn. At the heart of deep learning are neural networks, sophisticated structures inspired by the human brain. Imagine a network of interconnected nodes, each processing information and passing it on to the next. This network, with its intricate web of connections, forms the foundation of deep learning algorithms. By mimicking the brain's structure, neural networks excel at tackling complex tasks that traditional computer programs struggle with. Neural networks are revolutionizing fields like image recognition, natural language processing, and even medical diagnosis. They are particularly adept at identifying patterns and making predictions based on vast amounts of data. The power of deep learning lies in its ability to automatically learn features from raw data, eliminating the need for manual feature engineering. This ability to learn from data makes neural networks incredibly versatile and adaptable to a wide range of applications. Now, let's dive into the building blocks of intelligence layers, neurons, and activation functions. A neural network is composed of multiple layers stacked upon each other. These layers are the building blocks of the network, responsible for processing information at different levels of abstraction. The first layer, known as the input layer, receives the raw data, such as pixels in an image or words in a sentence. Subsequent layers, called hidden layers, perform complex computations on this data, extracting meaningful features and patterns. Finally, the output layer produces the network's prediction, such as the identified object in an image or the translated sentence. Within each layer reside numerous neurons, the fundamental processing units of the network. Each neuron receives input signals from multiple neurons in the previous layer. These input signals, weighted by the strength of their connections, are summed up within the neuron. This weighted sum then undergoes a transformation through an activation function, introducing non-linearity into the network and enabling it to learn complex patterns. Activation functions play a crucial role in introducing non-linearity into the network. Without them, the network would be limited to linear combinations of inputs, severely restricting its ability to model complex relationships. These functions determine which neurons fire and contribute to the network's output. Popular activation functions include the sigmoid function, which squashes the output between 0 and 1, and the ReLU function, which activates a neuron only if the input is positive. The choice of activation function depends on the specific task and the characteristics of the data. For example, the sigmoid function is often used in the output layer for binary classification tasks, while ReLU is commonly employed in hidden layers for its computational efficiency. The careful selection and arrangement of these building blocks, layers, neurons, and activation functions, determine the network's architecture and its ability to learn from data. Moving on to learning from mistakes. Training neural networks. Training a neural network is like teaching a child to ride a bike. At first, there will be many wobbles and falls, but through practice and feedback, the child learns to balance and ride smoothly. Similarly, a neural network learns by adjusting its internal parameters, those weights and biases, based on the errors it makes. This iterative process of learning from mistakes is what makes deep learning so powerful. The training process begins with feeding the network a large dataset of labeled examples, such as images paired with their corresponding object labels. The network then makes predictions on this data, and its errors are measured using a loss function. This loss function quantifies the discrepancy between the network's predictions and the true labels. The goal of training is to minimize this loss function, thereby improving the network's accuracy. Backpropagation, a key algorithm in deep learning, plays a crucial role in training neural networks. It works by propagating the error signal back through the network, from the output layer to the input layer. By calculating the gradient of the loss function with respect to each weight and bias, backpropagation identifies how much each parameter contributed to the overall error. This information is then used to update the network's parameters, nudging it towards making more accurate predictions. Gradient descent, another important algorithm, guides this parameter update process. It works by iteratively adjusting the parameters in the direction that most rapidly reduces the loss function. Imagine a person trying to find the lowest point in a valley. By taking small steps downhill, following the steepest descent, they will eventually reach the valley floor. Similarly, gradient descent helps the network find the optimal set of parameters that minimize the loss function, thereby improving its performance. Section 4. From Theory to Reality: Real-World Applications of Deep Learning. Deep learning has transcended the realm of research and permeated numerous aspects of our lives. From the mundane to the extraordinary, deep learning algorithms are quietly working behind the scenes, powering applications that we now take for granted. One of the most well-known applications is image recognition, where deep learning models achieve human-level accuracy in identifying objects, faces, and even emotions in images. Social media platforms utilize deep learning for facial recognition, automatically tagging friends and family in photos. Self-driving cars rely on deep learning algorithms to perceive their surroundings, identifying pedestrians, vehicles, and traffic signs. In healthcare, deep learning is revolutionizing medical imaging analysis, assisting doctors in diagnosing diseases like cancer earlier and more accurately. Natural language processing, another domain revolutionized by deep learning, enables machines to understand and generate human language. Virtual assistants like Siri and Alexa leverage deep learning to understand our voice commands and respond accordingly. Machine translation services rely on deep learning to accurately translate text between languages, breaking down language barriers and facilitating global communication. Deep learning is also used in sentiment analysis, gauging the emotional tone of text data, such as customer reviews or social media posts. This helps businesses understand customer feedback and tailor their products and services accordingly. The applications of deep learning are vast and continue to expand, pushing the boundaries of what's possible with artificial intelligence. Section 5. Conclusion: The future of AI. Deep learning, with its remarkable ability to learn from data, has emerged as a transformative force in artificial intelligence. Neural networks, inspired by the intricate workings of the human brain, are the driving force behind this revolution. As we continue to generate massive amounts of data, deep learning algorithms will play an increasingly important role in extracting insights, making predictions, and automating complex tasks. The future of AI is deeply intertwined with the continued development and application of deep learning. Researchers are constantly pushing the boundaries of deep learning, exploring novel architectures, training techniques, and applications. As these algorithms become more sophisticated and accessible, we can expect to see even more innovative and impactful applications emerge across various industries. However, the rapid advancement of deep learning also raises important ethical considerations. Bias in training data can lead to biased predictions, potentially perpetuating and amplifying existing societal biases. The lack of transparency in some deep learning models, often referred to as black boxes, raises concerns about accountability and fairness. As we venture further into the age of AI, it is crucial to address these ethical challenges and ensure that deep learning is developed and deployed responsibly. By fostering collaboration between researchers, policymakers, and industry leaders, we can harness the power of deep learning to create a future where AI benefits all of humanity.